This presentation provides an overview of Chapter 5, in the book titled, Simple G, a gridded economic approach to analysis of sustainability of the Earth's land and water resources. Edited by Iman Hakiki and Thomas Hurdle. And published by Springer. This chapter covers simple G model specification by looking at mathematical equations in a multi-scale, market equilibrium setting. This slide provides an overview of all chapters in the Simple G book, each of which has an accompanying presentation to motivate the material covered in that chapter. During this presentation, you'll see a simple representation of mathematical equations. Previous chapters laid the groundwork by providing essential theoretical foundations and general conditions for a quantitative geospatial economic model. Upcoming chapters will explore parameterization, data, and applications of this framework. The equations described in this chapter represent a multi-scale market equilibrium model. Each functional form is derived based on a set of assumptions about the behavior of economic agents in the food, land, and water system. They depict demand and supply as a function of income, prices or costs, as well as economic parameters, which have been previously estimated. In this chapter, we'll introduce 5 models of increasing complexity, which are all based on the same general assumptions and conditions. The main principle is to keep the model simple, yet with sufficient details for the research question at hand. With each new model, we introduce new inputs, markets, or features that may be necessary for the problem being investigated. Model 1 assumes a global economy with many grid cells, and represents a simple, but useful production function, which was covered in chapters 2 and 3. All of the agricultural inputs are aggregated into 2 categories. Natural resources, denoted by R, and the human input, represented by H. These inputs are combined in the production function using the parameter sigma, which represents the substitutability between these 2 inputs. The supply of natural resources is location-specific. In other words, they aren't geographically mobile, therefore local markets determine their economic return. The supply of human and manufactured inputs is determined at the regional level, which means they are geographically mobile and can move from one location to another based on wage incentives. This slide shows the linearized form of demand for the 2 inputs in percentage change form. The first equation shows that the percentage change in demand for natural resources depends on the percentage change in production, the substitution elasticity, the percentage change in the rent for natural resources, and the percentage change in crop prices. Similarly, the percentage change in demand for the human and manufactured input depends on the percentage change in production, substitution elasticity parameter, percentage change in the wages or costs of the human input, and percentage change in prices. The supply schedule for inputs is defined at different scales. The percentage change in supply of a given input depends on the supply elasticity, the percentage change in market prices, and a slack variable, which allows the user to shift supply outward or backwards based on policies or the dynamics of environmental and human systems. On this slide, you see 2 simplified versions of zero-profit conditions. You can view this as depicting the condition that unit revenue is equal to unit costs. Here, the percentage change in crop price or costs is the weighted average of percentage change in price of inputs. Theta depicts the cost share of an input. And these equations imply that a change in one input price will affect the output costs, and the magnitude of the impact depends on cost shares. More complex models follow the same logic, but their demand and supply equations include more variables and parameters to capture the relative changes in input prices. Additionally, land conversion decisions are captured by location-specific parameters that govern the degree of transformability of irrigated and rain-fed land. Note that the change in profitability of one land type can shift the supply of the other land type. For example, if the irrigation becomes more beneficial and the rent on irrigated land increases from point A to point B, as seen on the graph at the bottom of this slide, then the supply of rain-fed land shifts to the left. Adding more detail to the gridded agricultural production can be beneficial for specific research purposes, but would require additional equations and additional parameters. For example, Model 5 includes a detailed water module and therefore must also include mathematical equations for demand and supply for groundwater, surface water, and irrigation equipment. If you're interested in learning more about this topic, please review Chapter 5 of the Simple G book, where you'll learn about the 5 common models, their features, variables, and mathematical equations. Here, you'll find additional readings and references you might be interested in further exploring. On this slide, you'll find the link to the Simple G web page where you can find additional resources, as well as links to the book and other chapter presentations. Lastly, we also gratefully acknowledge support from the U.S. Department of Energy, the Department of Agriculture, and the National Science Foundation. Thank you for watching this presentation on the Simple G book, Chapter 5. We encourage you to explore the other companion videos that accompany the book on the Simple G webpage.